Hi, this is Jack Jackson. We're going to be looking today at Chebychev's theorem, and we're going to be looking at applying it to a particular homework problem. So here's a homework problem from the my stat lab. It says a survey of car rental agencies shows that an average cost of a car rental is 43 cents per mile with a standard deviation of 4.9 cents. So we know that the mean mu is 43, and that's in cents per mile. And the standard deviation is 4.9. That's also cents per mile. Okay, assuming we know nothing about the shape of the distribution, which is used to say something about the proportion of data close to the mean, and the answer is Chebychev's theorem. The empirical rule can only be used when the data is from a normal distribution, or at least approximately from a normal distribution. But remember, Chebychev's theorem says if we are if we go from mu minus k standard deviations to mu plus k standard deviations, and we look at that interval, so that's an interval from the mean, k standard deviations below and k standard deviations above, that in this interval we're guaranteed to have at least 1 minus 1 over k squared of the data. That's a fraction, which of course we could make into a percentage or a decimal if we'd rather. So at least this much of the data is in that interval. Okay, so we're going to use that fact here. So what percentage of the cars are between 27 and 59 cents? Well, this k is really a z-score. So we could have written it with a z instead of a k, because a z-score is how many standard deviations you are above, if it's positive, or below, if it's negative, the mean. So we're going to figure out a z-score for this. Remember, to find a z-score, you do the measurement minus the mean divided by the standard deviation. So we're going to do that for the first one, 27. So it's 27, so Z1 is 27 minus 43 over 4.9. I'll use a calculator here. 27 minus 43 divided by 4.9. So it's negative 3.265306122. Okay, the second z is, let's see, 59 cents. So replace the 27 with 59. So if I do second enter, pull that back up. Now all I have to do is replace the 27 with a 59. And notice that you get the same value. This question is designed that way. And so that's our k value, our z value in this theorem. So I'm going to store that as either k or z. I'll start as z. Okay? And so now what we want to do is we know that the percentage was within that is given by Chebychev's theorem. That's at least. So again, the interval is mu minus k or z sigma to mu plus z sigma. And it turns out that if we put in the numbers here, that we have a mu of 43, and then we put this z here, I'll round off, 3.265, and then times the sigma of 49 or 4.9, and then we do the same thing here with the plus. That interval is the same interval as the interval that we're given, 27 to 59. Okay? So, we have, the main thing is we have this z value that we need for Chebychev's theorem. Then Chebychev's theorem, if we do 1 minus 1 over z squared, this is going to give us what we need here. So let's just do that. 1 minus 1 divided by alpha z square, or previous answer square, and we get 0.9062109375 multiplied by 100% to get 90.62% roughly. Let's see, where did it tell us to round off? Actually, it didn't tell us where to round off. Okay, I think a whole number percent works here. We'll try it out. I'll try out on the problem. So about 91%. Okay, we'll check it in a minute. Okay, so that's the part B. Okay, so notice what we did is we found the z-scores for the n's. One will be just the opposite of the other. So that's the k value or z value in Chebychev's theorem. Then just use this formula to determine your percentage. So pretty straightforward. Okay, next thing, find an interval where we're guaranteed at least 63%. That's exactly backwards. This time we know that this 1 over 1 minus z squared, or k squared, is 63%. So, of course, we make this a decimal, 0.63, and we'll subtract 1. Okay, and I can do that in my head. That's 0.39 negative. Two negatives cancel, so 1 over z squared is 0.39. Reciprocal both sides, z squared is 1 over 0.39. So z is the square root of 1 over 0.39. I can do that in my calculator. The square root of 1 divided by 0.39. And that gives me a value here. That's my z, 1.6012815538. So that's my z or my k. Okay, and so you get mu minus k sigma. Let me just store that as k. Alpha k, or I could have used z. It is a z-score. And we want to go to mu plus k sigma. Okay, well, what was mu in this case? Mu was 43. So we do 43 minus that k times the sigma was 4.9. This will be the lower end of my interval. 35 point, well, it says round to the nearest cent per mile, which is about 35, okay, to a whole number here, because the units are cents per mile. And then we take this, the same thing that we just had, and just replace that subtraction with an addition. And, whoops, try that again. 43 was it? There we go. And we get 51. 35 to 51. Let's hope I got all the rounding off right here. 35, 51. This one says nearest cent per mile. The percentage didn't say where to round off, so we're going to try a whole number percent. Let's check all those answers. Very good. They all check. The rounding's good. And so that's how you do those problems. So part A was recognizing that since we don't know anything about the distribution, that Chebychev's theorem is what we need to use. And part B says we're given this interval, not this one, but an interval like this. We work to find the z-scores of those endpoints there, and they turn out to be opposites of each other, right? In this case, if they weren't opposites, we could go with the smaller one and just use the one with the smaller absolute value and use it. But in this case, they're the same, and so we can plug in this formula right here, with that particular z value and mu and sigma, and we can find the interval. That is the interval. So then we plug in this formula right here with that z value, and that finds the percentage. This one down here is exactly backwards. We know the percentage, that's just the part C. We plug that in, solve for z, which is our z or k value from above. Then we use this formula right here to plug in and get our result. And so there's an example of an application of Chebychev's theorem.